good morning to all. Now let us start with organic chapter, phenols and ethers. Let's go to that phenols. What are phenols? What is the difference between a phenols and alcohols? Let us start with that one. Phenols are actually the hydroxy derivatives of aromatic hydrocarbons. They are hydroxy derivatives of aromatic hydrocarbons. Whereas the alcohols are the hydroxy derivatives of aliphatic hydrocarbons. Initially, the phenols are also known as carbolic acids. But carbolic acids are actually the aqueous solutions of phenol. Now, there is a difference between phenol and phenols. Phenols means the class of compounds. Class of compounds which are the hydroxy derivatives of aromatic hydrocarbons, or where the hydroxy group, the OH group, is directly linked to the aromatic hydrocarbon. For example, benzene is a aromatic hydrocarbon. If the OH group is directly linked to the benzene ring, this becomes the phenol, right? And we have different number of the aromatic hydrocarbons like toluene, naphthalene, anthracene, etc. So in all such cases where the hydroxy group is directly linked to the ring structure, aromatic ring structure, we get phenols. Means it is a class of organic compound where the hydroxy group is directly linked to the aromatic hydrocarbons. But the first member of this family, where the OH is linked to the benzene ring, is simply known as a phenol. So we have this confusion in most of the students that phenol and phenols are totally different or one and the same. Phenols are a class of family, whereas phenol the first member of this family. Okay, now let us go to the classification of phenol. So classification of phenol. Phenol classification is done on the basis of number of hydroxy group present on the ring structure. If only one OH group is present, the phenol is known as monohydric phenols. Monohydric phenol means the ring contains only one OH group, only one hydroxy group attached to the aromatic hydrocarbon. For example, it is phenol itself. Or the another example, let us go for the phenols of toluene. Toluene, we know that for the benzene there is one methyl group already attached, right? If you take the phenol of toluene, then the second group, it is a disubstitution. So when the second group enters into the ring structure, we have three different isomers. If the second group is on the second position, entering into the second position, means this is the first. If you take, this becomes second, or if you take this as a first, this becomes a second, like that. This is the ortho case. So if the OH group is present and methyl is present, 1:2 position, this is ortho. This is called as ortho, and the phenol of toluene trivially called as cresol. So this becomes orthocresol. Or if the methyl group with respect to hydroxy group is present on the third position, here is a methyl group, this is meta position, this is called as metacresol. Similarly, we have got one more isomeric position is left out, that is the position 1 with the 4, what is called as para position, para cresol. So, in case of a cresol, that is a phenol of a toluene, we have got orthocresol, metacresol as well as the paracresol, right? And these two compounds, the phenol and cresol, they contain only one hydroxy group, so they are the example of monohydric phenols. So if suppose the aromatic ring structure contains two hydroxy group, they are known to be dihydric phenols. So let us take up the examples of dihydric phenols now, where two OH groups are simultaneously attached to the ring structure, aromatic ring structure. Example will be, let us take the example of a benzene phenol itself. If the OH group, now again the same type of complication comes with these compounds also. One group already present, the second substitution, it may be in the ortho position, meta position, or it may be on the para position. So we get three different isomeric diphenols, dihydric phenols. So if it is present on the ortho position, trivially this is known to be catechol. This is known to be catechol, right? If it is present in the meta position 1/3 position, this is told to be resorcinol, called to be resorcinol. Now the last remaining one is the para isomer or para position, where the two OH group is at 1,4 position, that is known as quinol. Right? So we have three different dihydric phenol with respect to benzene. If the two OH groups present in the ortho position, they are, that is catechol, or the OH groups present on meta position, it is resorcinol, and if the OH groups present at 1,4 position, para position, this is known to be the quinol. Okay, now let us go for the third type of classification. So the third one, if the three hydroxy groups are attached. Again, if we are taking the phenol of benzene itself, if the three OH groups attach to the benzene simultaneously, we call the phenols as trihydric phenols. So that is trihydric phenols. So trihydric phenols are the phenols where the three hydroxy groups attach to the aromatic ring structure. If that is possible, there are three options. One, OH group is present on 1, 2, 3 positions. Continuously consecutive positions, 1, 2, 3 positions. This is known as, trivially known as pyrogalol. This is known as trivially pyrogalol. Whereas if the OH groups are present alternative positions 1, 3rd and 5th position, this is known as fluoroglucinol. This is fluoroglucinol. And the last option, which is considered to be derivative of the quinol, where the OH groups are present on the 1, 3rd and 4th position, known to be hydroxyquinol. This is called to be hydroxyquinol, right? And if the OH group more than 3 attached, then they are known as polyhydroxyphenols. They are called as polyhydroxyphenols, means if the number of hydroxy group present in the phenol is more than 3. Now, let us come to the IUPAC nomenclature, IUPAC naming, right? How to name the phenol and phenols in a IUPAC method? There are 2 ways. Actually, in the book, one method is given. We can take the higher, like Dinesh publication, or if you go for advanced competitive exam books, there is another way of nomenclature. So I am strictly explaining now just the NCERT syllabus given for our PU board. Okay, so if you take the phenol, like the phenol of toluene, this is a one, right? I am taking one example, that is orthocresol. Cresol I am taking. The functional group is OH and CH3 becomes a substituents. So in that case, we can call it as, this is a number 1, 2, 2-methyl. It's a 2-methyl, and all phenols are the derivatives obtained from benzene, and OH group is almost like the alcoholic OH group. So we are replacing the E term by means of OL, replacing the E by OL, that becomes benzenol, right? So the name becomes 2-methyl benzenol. Benzenol is a name. This is 2-methyl benzenol. If the CH3 is on the meta position, it becomes 3-methyl benzenol. Similarly, the 4th position, likewise we can go for the IUPAC nomenclature. Similarly, if you go for catechol, it is a dihydric phenol where OH groups are present in 1,2 position, right? So this is 1 and 2, both are the functional groups. So the name will be benzene. Then replace the E by OL, but there is a 2 benzene, the phenohydroxy group, position number 1 and on the 2, so it becomes benzene 1, 2, 2 means di, and the functional group suffix will be OL. So it becomes benzene 1,2-diol. So if you take resorcinol, it is OH groups are present in 1,3 position. So name becomes benzene 1,3-diol. Or the last one of the dihydric phenol is the quinol, 1,4 position. This becomes benzene 1,4-diol. Right? So the nomenclature, IUPAC nomenclature is also simple. Here also we are giving importance to the OH as the OL, like in alcohols. Now come to the trihydric phenols, where the trihydric phenols we have taken 3 examples: pyrogalol, fluoroglycinol and hydroxyquinol. So pyrogalol 1, 2, 3 position. So the IUPAC name will be benzene 1, 2, 3. There are 3 OH groups, tri, and the suffix of the OH is OL. So it becomes benzene 1, 2, 3 triol. Similarly, in fluoroglycinol, main aromatic ring will be benzene. Then position number is 1, 3, 5. There are 3 OH, tri, and suffix will be OL, triol. Last one, it is hydroxyquinol 1, 3 and 4. So the name becomes benzene 1, 3, 4 triol. So likewise the names are going, right? Or you can, in this case, especially in this case, we are giving the importance to the OH group which are closer. So this is taken as 1, 2 and 4. So the name is 1, 2, 4 triol. Okay, so now there is another way of IUPAC nomenclature where we consider the OH has to be hydroxy group. Then the nomenclature I am taking only for these 2 set. This is 1 and 2. dihydroxy, 1,2-dihydroxy, then derivative of benzene, so this becomes benzene itself. Similarly, its name will be 1,3-dihydroxybenzene. But in some of the rare books, you may find this type of nomenclature also. Now, to avoid the confusion, universally, the first type of nomenclature, that benzene 1,2-diol, taking the OH group as a functional group and using the suffix -oil is accepted. But I am telling you because in some of the books you may find this type of using hydroxy group names also can be found. Okay, now nomenclature is over. Let us go for the next point, where we talk about the structure of the OH groups, or the type of bonding between the ring with the oxygen atom of the hydroxy group. So it is structure. Okay, so all of us in first PU classes covered about aromatic hydrocarbon, the structure of a benzene, where all the 6 carbon atoms of the benzene are in the state of sp2 hybridization. These all are in the state of sp2 hybridization. That is well known to us. Okay, now you take any one of the carbon atoms. There is no restriction that you have to use only this carbon or that carbon. All 6 carbon atoms are equivalent, and it is left to you as you wish. You can attach the OH group if it is monohydric phenol. Okay, I am attaching this one. Most of us feel comfortable writing the OH group on this carbon atom, or here or somewhere here. Okay, so this is written. That means O is linked to our sp2 hybrid carbon atoms. Whenever we come to the aromatic ring structures, we already covered some electronic effects. In the aromatic rings or in the conjugated systems or in arenes, we have especially the mesomeric effect or the resonance effect. And moreover, the oxygen atom has a lone pair of electrons. It has 2 lone pair of electrons. So this lone pair of electron is involved in the resonance. That means the lone pair of oxygen are not attached to only oxygen atom, present only on the oxygen atom. They are shifting towards the ring structure, giving different resonance structure. So as a result, this, if it is a possible of the resonance, we get a double bond between carbon and oxygen atom, unlike we write in the first structure. So this bond, that means the carbon bond with the oxygen is not purely a single bond. It has the character of double bond. So it is a double bonded, having the double bonded character. So the bond angle is nearly 109 degree. 109 degrees present. That is about the structure of the carbon OH bond. Now, from that, let us go for methods of preparations. So next is methods of preparation. How phenols prepared. Okay, let us go for one by one. A simple, and some of them are very, very important methods of preparation. So let us take the first method is from benzene. From benzene, how we prepare the phenol. Simple explanation, benzene is subjected for sulfonation. Sulfonation is done, so method involving sulfonation. Sulfonation means benzene heated with concentrated sulfuric acid or fuming sulfuric acid. It is strongly heated, right? So on heating, the SOH3 group, so I am writing the sulfuric acid in a simple way so that the reaction between a benzene and sulfuric acid can be easily understood and equations can be written very easily without forgetting. So each carbon atom has hydrogen. Between the two, we are removing a molecule of water, right? Now this position is occupied by SO3H group. That means you get benzene sulfonic acid plus water is obtained. Now this benzene sulfonic acid is fused with sodium hydroxide. It is a fusion, means heated to a very high temperature using the pellets of sodium hydroxide solid NaOH. This gives you directly the sodium salt of a phenol, ONA, sodium salt of phenol, what is called as sodium phenoxide, right? It is called as sodium phenoxide. So what is the difference now remaining between phenol and its salt is this Na. You replace the Na by H, we get a phenol. And basic parts, Na is obtained from the base that is removed using the acids. That is what we call as acidification is done. And the acidification is done, acidified, right? This is done by dilute acids. Dilute acids like HCl, you can use a H2SO4, but of course not HNO3. In organic chemistry, we just avoid the acidification with the dilute HNO3 because HNO3 in certain cases is acting as an oxidizing agent. So in all the acidification, you have to remember that HNO3 should not be used. So you can do it with either HCl or sulfuric acid, or instead of writing all these, you can just simply write H plus, or sometimes you can write H3O plus. Right? The basic part is removed and we get the phenol. Now this is the simplest possible preparation from benzene, sulfonation using sulfuric acid. The benzene sulfonic acid is fused with sodium hydroxide and it is acidified. You get a phenol, right? Now let us go for the second method of preparation. So first method is over. Let us come to the next one. Second method of preparation from diazonium salts. So we are preparing with diazonium salts, especially benzene diazonium salt. Di, you know very well, it is 2, means in the Greek it is nitrogen. So we are taking the aromatic compounds containing 2 nitrogen together and their salts. So very easily well known example is benzene diazonium chloride. This is very familiar. So let us see how to prepare benzene diazonium chloride. And the preparation is from aniline or benzanamine. You have to go for benzanamine or aniline, where NH2 group is directly linked to the aromatic ring structure. Right? It is aniline, benzanamine. This is subjected for the diazotization to introduce diazo group. And diazotization is done using nitrous acid. Remember, it is nitrous acid HNO2, not the nitric HNO3. It is not the nitric acid, it is HNO2 nitrous acid. But the problem with the nitrous acid is it is highly unstable. You cannot prepare it and store it in any bottle. Whenever it is required, you have to prepare it in the situation just by mixing the sodium nitrite with the dilute HCl. Right? So usually go for dilute HCl. One point is to prepare HNO2, or the aniline is basic organic base soluble in dilute acids. Therefore, especially we go for dilute HCl. That means this is obtained from a mixture of NaNO2 and HCl. Especially we take a bit of excess HCl where it can dissolve the aniline. The reaction is conducted at a low temperature between 0 to 5 degrees centigrade, or 273 Kelvin to 278 Kelvin. Right? Otherwise, usually diazotization move in reverse direction. You can say that the diazonium salt undergoes hydrolysis at a higher temperature. So reaction again becomes a simple here. I am taking H and Cl. Right? NO2 group has to be enter into the system. Already one N is present on the ring. This N also has to be attached. So overall, from these three chemicals, we are removing two water molecules. So try to write all this chemical in such a way to remove the two water molecule from this one, so that you can get the benzene diazonium chloride, Na2 plus. It is a salt, therefore we are writing NH2 plus and Cl minus plus two molecules of water. This is benzene diazonium chloride, which is yellow colored solid. Right? We get benzene diazonium chloride. So the next step is, from that itself, from the benzene diazonium chloride, simply add some water and warm it. Just warm it. No heat, mixing, boiling, etc. Just warm water is sufficient. This compound undergoes hydrolysis. Right? The N2 goes out, and out of O and H combines with the Cl, and OH come and link to the aromatic ring. It becomes a phenol. There will be liberation of nitrogen gas. Right? You get phenols. So this is a second method of preparation from aniline, or you may come across this again in the chapter of amines. Okay, now let us go for the third method of preparation, which is very, very important, especially from board exam. Okay, that is called as cumin process, cumin method. Okay, so this is a third method, very important one, and in most of the examination, board examination, we got this question either for 2 marks or for the 3 marks. So let us see, it is also very simple. We start from the cumin itself. Now what is cumin? Cumin is isopropyl benzene. Right, to the benzene, if the isopropyl group is linked, it is called as the cumin, and the structure is, if you remember the name correctly, you can write the structure by itself. So this is a middle carbon atom, isocarbon atom attached to the ring structure. Again, I am repeatedly saying this one, the structure, if you write properly, only then the whole method is correct and you can get the full scoring. Problem I've seen, or most of us seen while valuation, that most of the students, what they do is, instead of having the bond with the second carbon atom, central carbon atom, the bond will be like this. Either like this, or they write like this, CH3. Right? Maybe in a hurry-burry they forget where the bond should be there, but this structure cannot be taken as isopropyl. Moreover, the structure itself is wrong. For this carbon atom, the valency becomes 4. That is not possible. So while writing the structure of cumin, all students have to take care that the bond is between the central carbon atom, second carbon atom, with the aromatic or benzene ring. So cumin is taken, Cumin means isopropyl benzene. And through that we are passing the oxygen for about 100 degrees centigrade. The mixture is heated to about 100 degrees centigrade. Again, the process is very simple. All a student can logically remember to write the structure. So here is an active carbon atom. There is a bond between carbon and hydrogen. So in between that O2 will be come and insert. I am telling this one just to how to remember logically the reaction, right? CH3, CH3. So between the C and H, oxygen is inserted, O and H. Right? Now O2 is inserted. Now this is called as cumin hydroperoxide. This becomes cumin hydroperoxide. Okay. Now this compound is subjected for the hydrolysis by boiling with dilute sulfuric acid at about 100 and 130 degree centigrade. So just boil it. Right? Hydrolysis takes place. This much portion will be removed out. Again, this is a way to remember how to write the equation without mistakes. This much is removed and the OH group links the ring structure. Okay, so this will be OH. Plus this one CH3, COCH3. So we get CH3, COCH3, a very important byproduct, what is called as acetone or propanone. We get acetone or propanone, right? So we covered 3 methods now. One from benzene, that is by the sulfonation. Heating with sulfuric acid, the obtained benzene sulfonic acid is fused with sodium hydroxide, finally acidified. Second method is from benzene diazonium salt or chloride. Aniline is subjected for diazotization using HNO2 nitrous acid, but HNO2 is unstable. You cannot prepare and store, so used of that one you are using a mixture of NaNO2 sodium nitrite and dilute HCl. Then the obtained benzene diazonium salt is warmed with water to get the phenol. And the last third one we covered, very important one, is cumin. Cumin is isopropyl benzene, then heated with oxygen, which gives you cumin hydroperoxide, acidified, boiling with sulfuric acid, you get the phenol as well as very important byproduct, it is acetone or propanone. Okay, now the last one but not least, the last 4th method is also given. It is from haloarenes. Right? So let's start from how to prepare it from chlorobenzene. We are taking chlorobenzene and then the phenol conversion. This is a chlorobenzene. A simple way, you have to replace the Cl group by OH. That is done by heating with the sodium hydroxide. Are fused with sodium hydroxide, you get directly ONA, and that will be acidified with dilute acids, right? You get sodium phenoxide. On acidification, phenol is obtained, right? So the 4 methods are over. Once preparation is over, the very next step is studying its properties. So let us go for the properties, especially first is the physical properties. Let us go for physical property. In physical property, we come across the boiling point, melting point, either melting point if it is a solid, if it is a liquid, we go for boiling point, and then solubility, soluble in water or not, if soluble, the reason why it is soluble, etc. All the aromatic compounds, normally we do not have, most of the aromatic compounds are liquids. Then a bit higher one, they are solids. So phenol, the first member I am talking about, is a liquid, which has no color, no taste, no odor, etc. But when the phenol is exposed to atmospheric air, it starts to get oxidized and we get quinone. We get a compound which has a dark pink coloration, quinone. This quinone dissolves in phenol, so start imparting color to the phenol. So as much as time you expose a phenol to the atmospheric air, the color deepens. In the beginning, when the fresh bottle you use, it has no color, it is like watery liquid. When exposure starts, it gets a tinge of brownish color or reddish brown color. Slowly, as you use more and more times, the color becomes dark and dark. The reason is only the oxidation of a phenol by atmospheric oxygen, right? So it has high boiling point because of the ring structure. As the number of OH group increase or it become dihydric, their boiling point still goes on increasing. Now come to the point of solubility. The phenol, though we take it as an aromatic ring structure which is hydrophobic one, hates the water, but the OH group is present. Because of the presence of OH group, it can form the hydrogen bonds, intermolecular hydrogen bonds with the other phenol molecules. So you can have the intermolecular hydrogen bonding with the other, that is a H will be linking to the O, likewise it goes. Because of this intermolecular hydrogen bonding, the boiling point is quite high. One point. Second one, if the phenol group is present, that is OH group is present, and which can able to form the hydrogen bond not only with itself but also with water, because water also contains the OH, right? So phenol are able to form the hydrogen bonding even with water. Therefore phenol, to a certain extent, about 33%, phenol is soluble in water. Or the lower members of phenol, they are soluble in water only because the formation of hydrogen bond with water. One more point you can remember here, the easy method, that any organic compound which contains the OH group, normally soluble in water. 100% I won't say, but they are soluble to certain extent, certain percentage, and the reason is only one, that they are able to form hydrogen bond with the water and becomes soluble in water. Okay, and all the phenols, third point I am coming about his nature, corrosive nature, right? So phenol is highly corrosive in nature. If a drop falls on the skin, immediately you get bleaching type of, or it will be, you feel some burning sensation and you get blisters. A simple phenol with one OH group itself, we have that experience. As the number of OH groups present in the phenol increasing, trihydric are more corrosive, trihydric still more, and if you go for polyhydric phenol, they are extensively corrosive. Let's go for one example of polyhydric phenol, nature. Okay, let us come to the nature part, or where it is present. We all have the taste of cashew nuts, but we never see or we never experience how we cut these cashew nut shells to get that cashew nuts, right? The cashew nut shells, if we cut, those are the experience of cutting the cashew nut shells, I'm talking about them. Next 2 days they may find that their whole skin start to tightening up, changing the color, and finally the skin peels off. This is all experience for those who cut the cashew nut shell to get the cashew nuts, right? That means the cashew nut shell contains highly corrosive chemical, and that is nothing but the polyphenols. So polyphenols are present in cashew nut shells. Now you can understand the corrosive nature of the phenols. Okay, this is only the physical properties. Now, let us go for the next one, chemical properties. So, I'm talking about the next step, chemical properties. Chemical properties. That is, the reactions involving OH group, reactions involving the ring structure. Okay. So, reaction involving OH group or with ring structure, there will be two types. The reactions where O and H bond is broken. This is one class of reaction. Second class of reaction is where the C and O bond is broken. This is another type. So let us take the first one, the simple one where O and H bonds are broken while reaction will be involved with phenols. So let us take the first type of reaction, this type, breaking of OH bonds. OH bond, right? Simple few examples are given. Reaction with metals, with very reactive metal. We are taking only very reactive like sodium, magnesium, etc. Right? So sodium metal, when treated with a phenol, reacts. Right? This reaction probably we covered in alcohol also. All alcohols, when treated with sodium metal, there will be liberation of hydrogen gas. Same reaction also observed here, there will be liberation of hydrogen gas, and you get the salt of a phenol, it is O minus Na plus. This is called sodium phenoxide. Sodium phenoxide, liberation of hydrogen gas. Now this proves the similarities of OH group of phenol and the alcohols. So we usually teach, especially in lower classes, when acid is explained about the properties of acid. Acid is a substance which reacts with the base. Acid is a substance when treated with the metal, liberation of hydrogen gas takes place. So if you recall these properties, now we can say that phenol is able to replace hydrogen gas when treated with the sodium metal. So somewhere the phenol has the acidic properties. If it is acidic property, readily it must be reacting or it must be soluble in sodium hydroxide. And it is found to be correct that phenol completely dissolves in sodium hydroxide, forming again a salt and water. Right? So that means these two reactions practically prove that the phenols have acidic character. Now we have to explain theoretically how phenols behaves like acid or how do they have acidic properties. So let us go for acidity of phenols. Right, acidity, acidic nature of phenols. Okay, I am writing it. You can write C6H5 ring structure as such OH. Okay. Now let us recall the acid base theories of the first year classes. We have got different theories explained. One, Arrhenius theory, the primitive theory that was left out then. We took up the next theory, Bronsted-Lowry, Lowry-Bronsted theory, which says that acid is a substance which donates a proton, base is a substance which accepts a proton, right? And the third one we took is Lewis theory, which explains the acidic and basic character in terms of electron transfers. Now more suitable for this case, phenol case, is the second theory, Lowry-Bronsted theory, Bronsted-Lowry theory. Acid is a substance which donates a proton, Phenol has got H, right, hydrogen. If this H is given as the proton OH minus and H plus, or you can take it as a H2O, this H plus is donated, you can take it as HO3 minus. Now this is the phenoxide ion, this is a phenoxide ion. Now there is an equilibrium, it is not 100%, there is a certain percentage, it is a weak acid now, right, the pKa value is quite large enough, so it has a low acidic character. That is why equilibrium is existing. So this reaction, if proceeds the forward direction, that means the phenol donates the proton and forming phenoxide ion, then only phenol is acidic in nature. If it donates, means the reaction is proceeding in the forward direction. Okay. Suppose when this reaction proceeds in the forward direction, when it is possible? Only when the obtained phenoxide ion is more stable than phenol, right? If the obtained phenoxide ion is more stable than phenol, only then reaction is proceeding towards phenoxide ion or proceeds in forward direction, moves in a forward direction. Now how to say that phenoxide is more stable compared to phenol? How to say it? The explanation is done by using resonance structures, because aromatic compounds there is a resonance possible. So if we are able to write more number of resonance structures for any organic compound, as the number of resonance structure becomes more and more, the stability also more. So we have to try to write the resonance structure for phenoxide and also the phenol. So let us write the resonance structures for first one, phenoxide ion. Right, the minus is there, it is shifted. You know all how to write the resonance structures. When this is shifted, the neighboring double bond shift to the corner of the nearing carbon atom. So we get structure double bond O. This is shifted to here corner minus. The remaining two double bonds are intact. So the pi bonds are moving, delocalizing within the ring structure. So again this negative charge is shifting. Remember, it is not shifted back, it is shifted in the forward direction, clockwise direction, and this is shifted to the very next double bond. So when the double bond is coming to this position, this carbon atom gets more. Suppose you shifted to this here, this will be having a double bond. So this carbon atom gets the 5 valency, 5 bonds, that is not possible. So this bond is shifted to again the corner of the carbon atom, right? So one more resonance structure, minus is here now. This is shifted to this corner, remaining this one. So we got third. Now again the same, this is shifted to the nearest bond and this is to the corner. So I am writing the fourth resonance structure, double bond O, double bond, this negative charge is here now and negative charge is on this oxygen. Okay, now come to the last one, same one, and we get back the phenoxide structure in a similar manner, O minus, right? These are the 5 structures we wrote. The starting and ending you just observe. They carry, oxygen atom carries a negative charge, and the middle 3 structure, oxygen has got double bond. Okay, and the starting and the last 5th structure, the position of pi bonds in the aromatic ring is, you just observe, these are alternate positions. Okay, this is a 5 resonance structure. Now come to the phenol case. Phenol, can't we write the resonance structure? Can't we write? We can, because oxygen atom has a lone pair of electron and that is shifted here. When this is shifted to the corner. We get almost 5 types again. The resonance structure is a double bond here. It lost its pair of electron, carries a plus charge, remaining is everything. right? Again this is shifted and this is to the corner. We get the third resonance structure, double bond O plus, and this is a double bond minus double bond. Again shifting takes place and we get the fourth structure as such, minus sign here, double bond O plus, and shifting takes place. The lone pair of electron goes back to the oxygen atom OH as such, and we get the fifth resonance structure, right? Just a few minutes back I told, as a number of resonance structure we can write more, means stability is more. For phenoxide and phenol we wrote equal number of resonance structure. That means just with the number of resonance structure we cannot explain. So we are taking the next point. In the resonance structure of phenoxide, the oxygen atom either carries a negative charge or it has no charge. Whereas in the resonance structures of phenol, the first and last structure, first and fifth structure, oxygen carries a lone pair of electron and the remaining middle three, oxygen atom carries a positive charge. And all of us know that the oxygen atom is more electronegative element. That means it can have either the negative charge but not the positive charge. The positive charge is not acceptable on the oxygen atom. That means these three resonance structure reduces the stability of the phenol. Therefore, phenoxide ion is more stable compared to phenol, or phenol donates the proton forming phenoxide ion. That means it is acting as the acid, or it is acting as showing the acidic nature. Okay, so this is important point you have to remember. Phenol is acidic in nature because it is able to donate a proton. Why it donates proton? Because the obtained phenoxide ion is more stable than the phenol. That is explained by the resonance structure. In the resonance structure of phenol, the three structure, oxygen atom carries a positive charge which is not acceptable because oxygen is more electronegative. Therefore, phenoxide is more stable than the phenol. Okay, so we explained the acidic nature theoretically, and two, experimental practical one, that is reaction with the sodium or dissolution in sodium hydroxide, already been covered. Okay, now let us go for the next point. Next point is effect of substituent on the acidic nature. Effect of substituents on the acidic nature of phenols. Because in cresols we have got to additional substituent, or in dihydric, trihydric, or some other phenols. If the phenol has got one more group, then how its acidic nature is varied. Either it is varying or not, that we have to cover up. Okay, now let us go for the effect of groups. Already we have got two groups. One, electron donating groups plus I groups. We say plus I groups, electron donating groups. And another one is electron withdrawing minus I groups. Electron donating groups, we have the example alkyl groups. Remember this point, alkyl groups alone, only alkyl groups are electron donating groups or plus I groups. It can be methyl, ethyl, propyl or butyl, etc. As the number of carbon atoms are increasing in the group, the electron donating property increases or its plus I character increases, right? That means CH3 is a electron donating group, right? So let us take the example of the phenol where there is a CH3 group. and that is cresols. We are taking any one. I'm taking just one. I'm taking orthocresol as an example. Now we have to compare the acidic nature between phenol and cresol, which is more acidic in nature, right? So which seems to be more acidic in nature? Let us come to the point. The presence of CH3 increases the acidic character or decreases acidic character. A simple concept, easy answer also. So these are electron donating groups. So they donate the electron. That means they can increase the electron density on the oxygen atom, or there is a concentration of the electron on the oxygen atom, or you may say that wherever there is a accumulation of the electron or electron density increases, then the stability always decreases. That means here there is a accumulation of the electron, or electron density on the oxygen atom is increasing, thereby decreasing its acidic nature. So cresols are less acidic than phenol. Acidic than phenol. What is the reason? Reason is simple. CH3 group is electron donating. It donates the electron. As a result, the electron density on the oxygen increases. So electron density on oxygen atom increases, thereby decreasing the stability of phenoxide ion. Right? That is one portion. That means phenol is more acidic than cresol, or phenol has lower pKa value compared to cresols. Okay, that is one. Or if you take more and more number of CH3 group, then its effect is more and more acidic character goes on decreasing, pK value goes on increasing. Or even you can take the example where instead of methyl there is one ethyl group which contains two CH carbon atoms or CH2CH3. The electron donating effect is still more compared to CH3, therefore its acidic character is less than even cresols. Okay, now let us come to the next one. It is about electron withdrawing groups. Electron withdrawing groups minus I groups. Right? Remember, except alkyl groups, all other we consider to be electron withdrawing groups, like the presence of OH, Cl, NO2, CHO, etc. Right? These all are electron withdrawing group, either as minus I or it is a minus M. With the mesomeric effect, they draw the electrons. Okay, now let us take the example of phenol, right, one by one, and nitrophenol. Nitrophenol, it can be on ortho, it can be on meta. Let us come afterwards a discussion about ortho, meta and para. Nitrophenol separately. And also one more example of chloro, presence of Cl. Right, three are taken. Which is more acidic and why? The question is important one, especially board examination. Not only board, even CET you can have such type of questions. They give a set of phenols and ask to write which order, writing the order which is ascending or descending order of acidic character will be asked. To answer that question, you should know the basic concept behind this. See, OH group is common now. Okay, the extra is nitro group here and Cl. It is also electron withdrawing. This is also electron withdrawing. Right? But one more thing is, this has a minus M effect and this involves the nitro group, you know that one. You can write the structure like this, O and minus. This involves in the resonance structure of the ring structure. Resonance structure of aromatic ring benzene. Means if NO2 groups are present, you can extend the resonance structure involving NO2 groups. So compared to chlorine atom, chlorine, NO2 is a stronger electron withdrawing group. So as the strength of the withdrawing group increasing, the acidic character also increasing. Therefore, nitrophenol is the strongest acid. Then this is the second place, this is the first one, it's the second one, and the least will be, weakest acid will be the phenol. So this has the lowest pK value and phenol has the highest pK value. Now let us come to the point of ortho, meta and para nitrophenol. Try to compare the acidic characters. Right? So let us go for that one. Acidic character of the three ortho nitrophenols. Okay, this is a one. And meta nitrophenols. And the last one is para nitrophenols, which is more acidic, and the reason, right? In this case, all are nitro groups. So we may expect that they have the same acidic character. No, they don't have same acidic character. One point I already mentioned, this is in the ortho position, so you can have more number of resonance structure involved. Why can't this with, is it not in the ortho position? And we have seen in case of writing the resonance structure of a phenoxide ion, this is shifting like this. So here ortho position, again it is possible to have a resonance structure. Here also you can have, but there is one problem with this structure, because this is a OH and there is a O, you can have the intramolecular hydrogen bonding possible. So because of the intramolecular hydrogen bonding, the resonance structure what we write like this in case of para may not be possible in the ortho. Right? It is electron withdrawing, of course it is electron withdrawing, it increases the acidic character also, but not as the para position. So para compounds are strongest one, this comes probably second one, and in the meta we cannot write the resonance structure at all. Not possible at all, because in writing the structure we have shown in the third position there is no shifting of electron takes place, meta position, there is no change in the electron density while writing the resonance structure either with the phenol or phenoxide ion. Right? So third comes this one. As the number of NO2 groups on the phenolic structure increases, we get acidic character also increases. That means if you take nitro compounds, nitro, if its two groups are present, then compared to mono it is stronger. Again, if the three nitro groups are present, we have taken 2, 4, 6 trinitrophenol. This is 2, 4, 6 trinitrophenol, because we come across, no, because we are going to come across this one in next points. So this is very strong acidic character, and this is known as picric acid. This is very familiarly known as picric acid. Right? So we clear that the presence of electron donating group reduce the acidic character. The presence of electron withdrawing group increase the acidic character of the phenols. As the number of either donating or withdrawing group increases, their character as well changes. If it is a withdrawing group, the number of electron withdrawing group increase, acidic character goes on increasing. So 2, 4, 6 trinitrophenol has highest acidic character, whereas if the electron donating group increases, their acidic character goes on decreasing. So we covered important points related to the acidic nature of a phenol, and we come across so many questions either in CET or in board examination related to this point. It is important concept. Okay, so these are the points for the reactions involving breaking of O and H group.